So in this video, we're going to talk about principal planes and the effective focal length of a system, or EFL. And first of all, what's the motivation behind this? Well, we know if we've got a thin lens, we know it's characterized by its focal length and just where it's located in an imaging system. And we know if we've got an object over here, it's probably going to get imaged to maybe something over here, or maybe not. I don't really know. But it's fairly simple, right? We've got some object distance, some image distance, and we've got pretty simple relations between to figure these quantities out. So we've got our imaging condition, and we've got we can also easily calculate magnification. So thin lenses are pretty simple. We like thin lenses. They're great to deal with. But what if we've got some arbitrary optical system? So I don't know, maybe we've got a converging lens and then a diverging lens and then another converging lens. And we've got some object, some distance away from the first lens. Let's call that S1. This is going to be a little more challenging to analyze than a thin lens, right? We have to calculate the transfer matrix for this whole system, and then we can use the imaging condition T12 is equal to 0 to figure out where the image is formed, and it's a little more complicated. So we can ask ourselves sort of a crazy question. Is there a way we can treat this like a thin lens? Can we turn this whole optical system into something that we can just treat like a single thin lens? And that's an interesting question. It's sort of a little crazy, right? Because, I mean, you've got three optical elements here. It's not just one lens, and there's some distance between them. And I don't know, maybe this lens is a thick lens. So how are we going to do that? Like, it would be great if we could, but it seems a little weird. Well, I mean, what do lenses do fundamentally? Like, how do we characterize them? We know they're characterized by, we said, their focal length. And we can figure out what the focal length is by sending in some parallel rays and then tracing them through the system. So let's say that we've got a converging lens, a diverging lens, another converging lens, and let's say they focus the rays to a point, let's say here. So, I mean, this whole system is sort of acting like a thin lens, right? Because it's taking a bunch of parallel rays and it's focusing them to a point. So what we'd like to do is we'd like to find the equivalent thin lens. So if we say we put a thin lens here, maybe that lens acts exactly like this whole system in that it focuses to the same point and it's got the same angle. It's got this same converging angle theta. So maybe we can take all these lenses and simplify them into a single lens. And obviously this won't act like the same optical system everywhere, because if we look at what the rays look like here, on the bottom there are still parallel rays, but on the top they might be some ugly converging or diverging angle we don't really know. So this is only going to be valid inside or outside the optical system. So outside these boundaries of the optical system. And so we call this lens location here, where we have our equivalent lens, the principal plane. The principal plane. And we call this distance from the lens location to the focal point the effective focal length. Sorry, principal plane. And this is sometimes referred to as the second principal plane because it's going from the front to the back. I guess that's why people call it the second principal plane. And so this would be cool if we could do this, but how do we actually find where the principal plane is, and how do we find the effective focal length? Well, we said these systems should look exactly the same from the outside, and so we should have something that looks like, well, parallel rays, until we hit the effective, or until we hit the principal plane, at which point our parallel rays should start converging and acting like they're the rays from this first system. So in this imaginary thin lens system that we've created, the rays are actually parallel until they hit the principal plane, and then they start to converge. So that's how we're going to figure out where exactly this principal plane is, because it's just going to be the intersection point of these outgoing rays and the incoming parallel rays. So the rays that we sent in at the very beginning and the rays that start to converge, that we sort of backtrack them to the principal plane. And that's how we're going to figure out where it's located. So how do we find a mathematical expression for this? Well, what we're trying to say is that when we send in an input ray of some height, so its vector is x in 0, and we act on it with the transfer matrix, both of this top system and the bottom system, that we get the same thing at this effective focal length, or at this focal point. And we get the matrix 0 and then some angle theta out. We don't know what it is. We don't really care. In other words, we can write out this system of equations as 0 is equal to t11 times x in, and theta out is equal to t21 times x in plus what is this, t22 times 0, because t22 times theta in. And so just for completeness, I should also have t12 times 0. But we can erase both of these because they're 0. Theta in we've defined to be 0 because we're sending in parallel rays with no angle. And so the first equation says, well, we want t11 to be equal to 0. So t11 should be equal to 0 because xn can be whatever we want. We can send in a ray up here, a ray here, a ray here. So for all xn, this equation has to be true. So t11 has to equal 0. Okay, that's interesting. What about this second equation? Well, this tells us what theta out is. And we said that theta out has to be the same. Theta out has to be the same for our definition to work out properly. And this means that t21 of the two matrices has to be the same. And so what is t21 of, let's assume that we know t21 of our initial system because we probably calculated the focal point, we probably calculated the overall transfer matrix. So let's assume that that's known. What's t21 of this system, so this thin lens? Well, we know it's just the propagation matrix by the distance of the focal length times the lens matrix, because first we are going through the lens, so first our parallel rays are going through the lens, and nothing happens to them between here and here, so we don't care about this distance. So first they're going through the lens, and then they're propagating by a distance f, because that's or by a distance EFL. Here I've just abbreviated that as f. And so we can write out what that is. We know the propagation matrix, we know the matrix for a thin lens, and you can do the math and you'll get that the matrix looks like this: 0, f minus 1 over f, 0. And this satisfies our first condition that t11 is equal to 0, so that's comforting. That means we've got some consistency. And t21 here, you'll see t21 is just minus 1 over f. So this tells us what our focal length of this lens needs to be, and what the distance is, because we said that was also just f for the effective focal length. And so if we rearrange this, we'll get that f is just equal to minus 1 over t21. And this is our answer. This is the effective focal length. So if we have our original transfer matrix, the transfer matrix of our lens system, we can calculate the effective focal length almost trivially. We just take -1 over the reciprocal of t21. And that's sweet. That's super easy. And if we know the focal point, we know that the principal plane is just going to be an effective focal length away from it. So, and presumably you'll know that because when you've analyzed the system the first time, you'll find the focal length, or the focal point. And so just for completeness, we can write the location of the principal plane is just our original focal point, which we calculated previously when we were analyzing some lens system, minus the effective focal length. And so great. If we analyze these lens systems using transfer matrices, you see how easy everything becomes. The effective focal length and other aspects of the system are just trivial to analyze. We just literally grab one of the components of the matrix. So I hope you enjoyed the video. If you have any questions or comments, please post them down below. If you like the video, please give it a thumbs up and consider subscribing to my channel, and I'll see you next time. Thanks.